Okay, so I am going to work the exam 4 review that is posted online. And so we're going to do a correlation, a regression, and a multiple regression. So we're going to start with correlation. So we're looking at math ability to believe that math ability is innate, which is perfect for this class. The first thing it says to do is make a scatter plot. So I'm going to take this data and open Excel. And create an Excel file that includes this information. So the first one's math and the second one is belief. Paste that. And so I want to make sure these are numbers, just so it imports correctly. And generally you can tell that they're a number because they will right align naturally. It was centering them, but when I turn that off, it shows that it's right aligned, which means it's a number. If you see something that's left aligned, it assumes that that is text, like this. And so sometimes if you accidentally add spaces in front of the number, it will freak out. And that's just the cutting and pasting issue with Excel or Word to Excel. So let me stick this in the right folder. So we're going to save this as a CSV. It's a correlation example. So we'll come over here to R. I'm going to import that. So import dataset from text file. Gotta find the file now. Folders and folders, right? Here's correlation. I'm gonna make sure my header's turned on and click import. Copy this in case I need it later. So I've got my 2 columns and now I want to do a scatter plot. So I'm going to load ggplot. And if we don't want to clean it up, we can do just build the plot. So let's build the plot first. So scatterplot equals ggplot. The dataset name, so correlation, aesthetic, column names. So let's see here. Got math, comma, belief. And this is a scatter plot, so it doesn't matter what the order is. And then without cleaning it up, I could do scatterplot plus geom underscore point. And what that will do is make the scatter plot. And then I would want to clean this thing up. So I'm going to open the R script that's online that you'll get on the test. Make this a little bigger. Now scatter plots are right here. Okay, you don't have to add the line of best fit for this particular one, but we also have that crazy theme coding. So let's copy that. I'm gonna dump that right here. Whew, it's a giant line. So one quick thing, and I will fix this online, is that I think ggplot updated and now it has to say this. At least mine did. And I'll fix that in your R script for you. So if I want my plot to look nice, I can add the theme. And that just like makes it a little bit more readable and cleaned up. And then another thing we can do is add X and Y axis labels. So that is XLab. Make this a little bigger here. So math ability and YLab. Quotes. Belief math is innate. So that would be the kind of plot that I was looking for. So you would just cut and paste that into your Word document. Describe the pattern of association. So in this part, what I'm looking for, is it positive? Is it negative? And in this particular case, it looks negative. So as your math ability increases, your belief that it's innate decreases. So this is a negative correlation. And then the 6 steps. So step 1 is our assumptions. So x and y are scale. Well, it didn't really tell us the scale of them, but I would believe so. So they're at least interval. X and y are random. No, sorry. What's the word? Normal. Okay. Can't assume because n is less than 30. Random selection, that would be really hard. And definitely no random assignment. I can't randomly assign you to a math ability. Other thing we want to check for is homoscedasticity. And on that, what you can do is draw a line, where's my squiggle line here, around the dots and see if that makes a fairly even distribution. And I would say yes. Kind of looks like a dinosaur. Okay. So the spread is approximately the same all the way across x and y here. Step 2 is the research. So math and belief are correlated, where r is not equal to 0. And the null is that they aren't correlated. I don't know what that word is. There we go. Where r does equal 0. Now step 3 is where I get the actual correlation. And well, we've got to figure out degrees of freedom for step 4. So to do the correlation, it's core.test, and then x, math, and y. Now you can switch these, remember, because it's correlation, so that doesn't matter. So you can copy this output if you'd like. So our correlation is down here under core. So negative 0.91. So that's a very strong negative correlation. And our DF is 4. So remember it's n minus 2, but here it is here, just in case. In step 4, we want to get the critical score with 4 degrees of freedom. So that is QT 0.05. I'm not sure the problem said, actually. That's just, nope, there it is. Good. So 0.05 here. Okay. 4 degrees of freedom. Lower tail equals false. Now this is a two-tailed test, so I have to divide by 2. Okay. Pretty much all of correlation and regression is a two-tailed test. It's got 2.78 plus and minus 2.78. This is a two-tailed test, there have to be 2 of them. Step 5 is t found. Well, we already got that. So 4.61. So step 6 is t found more extreme than step t critical, step 4. So 5 more extreme than step 4. Negative 4 is more negative than negative 278, so I would reject the null. There is a correlation. So that would be the 6 steps for a correlation test. Now, if I go on to a regression test, so this is a simple regression because I only have 2 variables. So let's copy these. Make a new Excel file. So let's call this regression 1, because we're going to have 2 of them. CSV. Save. Continue. Close these real quick. Let's import that data set. So import from text file. Goodness. Find our folder again. Okay, now that looks good. So what's the first thing we got to do? Write out the regression equation is what it says. So you have to run the linear model first. So when you're looking at your R script, let's go down to the bottom here. Let's keep going. Critical values, here we go. You're going to be using this code for regression test. There goes. So we have to change this to the DV. Well, which one's the DV? Let me go back and look at the problem. So we're looking at whether the familiarity of words predicts their time it takes to press a button. And the idea that more familiar words would be easier, so it would be faster. So that's actually a negative correlation. All participants were given the same words. Ooh, grammar. Familiarity words was rated on a 1. Was rated at a later time on a 7-point scale. English is hard in this one. High is more familiar and the scores listed below. Okay. So it doesn't totally make it clear, but we're looking at familiarity of words predicting response time. So anytime you see, and here I'll just write this out as right here. Using X to predict Y, or X should predict Y. Those are the kind of formats that you'll get where X predicts Y. If they do it in the reverse, they say Y is predicted by X. So make sure you got your X and your Y in the right order, or you will get some of this wrong. So we're using X to predict Y. So X in this case is familiarity. Y is response time. And with that, Y is on the left here, so it's familiarity. I'm sorry, I just did that wrong. Response time. The IV is familiarity. And our data is regression 1. So I'm going to copy this coefficients part. That's the only part I really need. So X predicts Y. So remember, in the LM output, it does Y is approximated by X. So don't get these backwards. So write out the regression equation. Well, given this output, I want to look at here under estimate. First one's A, second one's B. So the regression equation is Y equals 4.04. So we have a general score of liking things by 4 points, minus 0.4748 if I round up X. So for each familiarity, half a familiarity point, we're, for each familiarity point, we're decreasing our response time by 0.48. So we should be faster at words that are more familiar. So the next question is the 6 steps. But let's do C first, because that one's kind of easier to do right here. So predict the reaction time or response time for a person who rates this familiarity as a 5. So we're going to say Y equals 4.04 minus 0.48 times 5. Great thing about R is it's a math machine, so it's 1.64. Now, does that make sense? Okay, so if I go up here and I look at these, so if I read it as a 5, their real response time was 1.75, but this is an estimated score. So that score makes sense because it's in line with the rest of the data. Let's do the steps and then the plot. So step 1 is the same, so X and Y are scale. Yes, both are ratio scales. Wait, no, the Likert scale is not. So 1 is interval and 1 is ratio. So, but they're at least both scale. X and Y are normal. Oh, definitely not. Not only is n less than 30, response times are never normal. Let's see. Random selection, that's unlikely. And random assignment, I can't randomly assign you to like words, so that's unlikely as well. We'll look at homoscedasticity after we get the plot. Spelling. So for step 2, what we're going to do is say familiarity predicts response time. This is the research. Or that B is not equal to 0. And the null is that familiarity does not predict response times, or that B is equal to 0. Step 3 is to include the output for the equation. Well, we've already done that, so we would copy this. The other thing we want to do is get beta. Now, beta is R because we only have one variable. But when we have multiple variables, beta is pretty helpful. Okay, so we're going to load quantsci. And the code for that is lm.beta of your output. So whatever you called output up here. So familiarity is 0.97. So it's nearly a perfect correlation. So for step 4, we're going to find the critical score. So we also should probably list degrees of freedom. Our degrees of freedom is this one here. Or n minus 2. 1 for X, 1 for Y. So what are we using? 0.05? Yeah. So we're going to do QT. Oops, not down there. Up here. So QT 0.05 divided by 2, because it's a two-tailed test, equal to and not equal to. 5 degrees of freedom. Lower tail goes false, so we get the positive one. It's 2.57. So it's plus n minus 2.57. Step 5 is t found. Well, that's actually here in the output under t value. It lines up better in R. So let's go back and look at that. Okay, so here's t value using this one here under familiarity. So negative 8.7. And then step 6, do we reject? Yes, reject null. Because 8.7 negative is more extreme than 2.57. Remember, you can use the little stars as a cheat. Okay, so we haven't answered that homoscedasticity question, so let's try that. Alright, and I haven't included the plot code yet in my R script, so I'll need to update that. But one thing we can do is, since this only has one X and one Y, we can do this as the same, we can create the plot in the same way that we did above for our scatter plot. So I'm just going to copy this. Come down here. So I've got ggplot open already. We want to use the regression data set. Oops, regression 1. And I just want to make sure I get x and y correct. So x goes first. So if it's something, comma something, x, comma y, if it's got a tilde, y is on the left. Okay, just like we write y hat, let me go back here. Y equals blah 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 x. It's the same when you write the output, the LM code. You do y equals blah 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 x. It's just it uses a tilde and not the equal sign, because you're estimating rather than setting it to something. So x in this case is familiarity. Y is response time. And so there's our graph. If you want to, you can add the line. You don't have to, but it does help a little bit with that homoscedasticity question. Okay. And so it's pretty easy to see. It's pretty good around the line. Okay. So let me include this plot, because this is technically what you have to get credit. Go back, look at this one. And then let's go back and answer our homoscedasticity question. I would say yes. Alright, so the last thing we're going to do is a multiple regression. And it's a similar type of thing to the familiarity question. So we can predict how high someone's going to rate a word based on how well they type them on a computer. So the Cordy effect is that words that are more pleasant are, words that are typed more with the right hand are more pleasant, and this is a similar idea except based on how well you can type them. So we should like words that are easier to type. It's embodied cognition research. So but it's also important to control for letter and word frequency, because we've already seen that familiarity influences ratings. So which predictor seems to be the best using p less than 0.05? And the first thing we want to do is write out the equation. So I'm going to take all this and make myself my Excel file. So let's do File, Save. So this is Regression 2. Save. Yeah, I know. And that should work, so I'm going to close Excel. Let's go back to Studio here and import the file. Import dataset from text file. Find our file here. Oop. Regression 2. Okay, all that looks good. So now I've got my file imported. So from there, what I want to do is run my LM output that I did a minute ago. So we're going to take this idea here and do it again down here, but with more variables. So we're going to save that as output, so we don't need that original output anymore. The DV goes first, so we're predicting their ratings with, and then in any order. So letter frequency plus word frequency plus typing speed. And our data is stored in regression 2. Now let's get a summary of that output. So summaries, it's gonna be a little bigger this time because we've got several different things. I'll cut and paste that output into here because we're gonna use it again in a little bit. Now, if I'm writing out the regression equation, what I'm gonna do is y equals, and it's the first one in each of these columns. So there's A, and then here's B for letter frequency, B for word frequency, and then B for typing speed. So we're going to say y equals 6.07 is our base rating plus 0.07 letter frequency plus 0.23 times word frequency plus, or it's actually minus 0.09 for typing speed. So that's the regression equation. Let's also get those beta values. So lm.beta, because I already have the output open, quantsci open. If you don't, because you didn't do the previous question, be sure you open quantsci first. And so which predictor is best? Well, it's clearly word frequency is the best predictor because it has the highest beta value. And so that's why beta is so important, is because these are scaled based on the scale of the data. And clearly typing speed, letter frequency, and word frequency are not the same scale, so it's not fair to compare them directly, but with beta we can, because beta is a z-score. So it can get bigger than 1, and it can be negative. Okay. At this point, it's not a correlation because I have more than 1. 6 steps and then a scatter plot. So let's try those steps. So step 1 is our assumptions. X is and Y are scale, and I'd say yes, they're at least interval. Okay, the frequencies are and rating are, the frequencies and typing speed are definitely ratio. That could be 0. The rating is probably interval and not ratio. So X and Y are normal. Okay, we'll go with no, n is less than 30. And a lot of these data are non-normal. Random selection. Can't randomly select people really here because it's anyone that can type. And I can't really randomly assign you to a typing speed. Okay, so this is a correlational test, a correlational experimental design, but a regression test. Because remember, you got to keep those two things separate. Last one is homoscedasticity. And we'll come back to that after we have our scatter plot. So for step 2, we're going to say the research is that letter frequency. The table's really squeaky. Let's see if I can make it stop. There we go. Letter frequency, word frequency, and typing speed will predict ratings. So B's are not equal to 0. And the null is all that stuff does not predict ratings. So B is 0. So that's actually 3 different hypothesis questions at once, but it's easier to write it out this way. Okay. Step 3 is all the stuff we've already done. If I can spell, good gracious. So it's all of this output. And the betas. And then degrees of freedom. Thankfully, degrees of freedom is listed right here. But if I had 15 people, which is what I think we have, right? Come over here, 15 observations. Why is it 11? Well, it's 15 minus 1 for Y, minus 1 for X1, x2 and x3. So it's 15 minus 4. So it's still 1 for y, 1 for x, but there are a couple of extra x's in this example. So df equals 11. So in step 4, when we find the critical value, we're going to do qt. Come all the way down to the bottom here. So I got qt 0.05, I think, divided by 2, where 11, the lower tail equals false. So I got 2.20. So it's plus and minus 2.20. So in step 5, we have to do a couple of these. So for letter frequency, okay, T was here, 0.518. Word frequency, T is 1.94. And typing speed, the T value was negative 1.06. So there are 3 of them because there are 3 predictors we're testing here. So you notice none of them have little stars next to them. So none of them are at least 0.05. The little dot here means that it's close to 0.05. And so for step 6, we fail to reject the null for all predictors. It might be that one is predictive and the other is not. So talk about each one separately unless they're all predictive or all not predictive. So which one's the best? Well, word frequency is the best, but none of them are significant. Last thing is to include a scatterplot. Now, I paused and went back and added this for to your R script. Oop, wrong window. So we would open ggplot, and what we would do is save the predicted values. So this output.fitted values does not change unless you called output something weird. And that's their predicted score on ratings given all 3 variables at once. So I'm going to change this to the data set we're using. So it's regression 2, predicted score from here, and then whatever y is. So y is rating. And then we can add the line if we want. That's this code. Mine didn't copy very well, but I also definitely want to add an X label. So that's predicted score. And then a Y label, which is rating. So let's do it without the line first. Can also add our theme here, so it's pretty. So here's their predicted score versus their actual score. Oops, didn't mean to put that in the middle of the sentence there. And I guess it's slightly positive. So as their predictors overall go up, or ratings go up, but it's kind of hard to tell. So I could do 2 things here for homoscedasticity. I could take and just draw a line around it. You don't actually have to draw this line, but I don't know, it helps me. And, you know, regardless of the fact that I missed this dot down here, I say that's actually pretty even. So I'd say homoscedasticity has been met. You can also add the line. So geom smooth, method equals ln. If that helps you a little better. So the spread, if you look at it this way, it doesn't quite look even, but you gotta kind of ignore the confidence interval band. We've only got 1 dot that's kind of like outside the close range. Either plot is fine. All right, so let me go back up here and say, yes, it's close. Okay. If you get a plot like the ones we got in class, those are really bad. So that would be how you'd work a multiple regression with the 6 steps.